we have our, say, unit normal vector. Okay. Then because a unit normal vector, so that's basically your velocity divided by length of velocity, right? So because it's of length 1, its derivative vector is going to be perpendicular to t. So t prime is perpendicular to t, right? Because you can see it, t times t equals to 1, and you do your product rule, and you'll get t prime times t equals to 0. Okay, so that's perpendicular. So let me try to draw a picture of what is going on. So we have our curve. Then we pick a point on the curve. Then we draw our vector t. Okay. Then we draw t prime, which is going to be perpendicular to it. Okay. And what we'll do is we'll take a unit vector in direction of t prime, and we're going to call it normal vector. Basic normal vector. Basic normal vector is going to be essentially it's your t prime. Only thing is you want them to be unit. Okay, that's it. Okay. So now you basically have your n right here. It's the same, but maybe of different magnitude. Okay. Maybe a little bit longer, a little bit smaller, but that's essentially it. Okay. So basically the way you want to look at the picture now is, so t is your tangential vector, and t prime is essentially your kind of something which is responsible for acceleration. Okay, so in a sense, when we're talking about natural parameterization, that is essentially your acceleration. Okay, so where you want to look at it is your t and your acceleration, they kind of in the same plane. Okay, so we're in the same plane. We're on the same plane. We live on the same plane. And then what is going to, then we're going to get, we're going to take the cross product. So if I take t, take a cross product with n, I'm going to get binormal vector. Okay. So on the picture which we have here, it's going to look t to n, so rule of thumb, so it's going to look something like this. So that's binormal vector now. So to an extent is that's something which around which we're going to be rotating our kind of path. Okay, so that's kind of axis of rotation. So around this one, it's kind of rotates to an extent. That's how you might think of it. Okay. Okay, so that's perpendicular to the plane around and on which our movement is happening. If you do your approximation, so kind of doing straight line approximation in this case, plane approximation. So we kind of, if we zoom in locally, then it's going to be movement on the plane, and then it's going to be rotating through the plane. And binormal will tell you where it's rotation. At least that's an idea. So that's what it is. Okay, so what we'll be concerned about how to calculate normal vector, how to calculate binormal vector, and how that relates to acceleration. Okay, so let's move on. Unit tangent vector is basically your derivative divided by speed, velocity over speed. Okay. So from here we obtain that velocity times this is, so velocity and the unit tangent vector in the same direction, we're only off by magnitude of speed. Okay. Then we can find acceleration, taking derivative of that expression. So we're going to get derivative of speed plus speed times derivative this way. Now what we have here is t prime. And you recall what normal vector is. Normal vector is essentially your t prime, but unit vector in the same direction. So the way we might look at A now is we can write it as a linear combination of two vectors, tangent and normal, t and n, and some coefficient here, we'll call tangential coefficient plus normal coefficient. Okay. So that's how we might look at it. Again, so all the movement, basically, if you locally approximate it, is going to be your velocity and your acceleration based in the same plane with t and n. Okay. Okay. And now let's see how we're going to find AT and AN. So to find AT and AN, first comment, t and n are perpendicular, right? Because t and t prime are perpendicular. So velocity cross acceleration is going to be velocity cross at t plus velocity cross an. This part is going to be equal to 0 because velocity is parallel to tangent vector. Is speed times tangential cross n. What we got is length of v cross a is going to be equal. So left side should be equal to length of the right side. So length of v. I can push an outside. I can push constant outside. So what we get here is basically vector v, length of speed times an times t cross n. And t and n are perpendicular, and they are unit vectors. Because they're perpendicular, t cross n. Length of t cross n is going to be length of t times length of n times sine of angle in between, which is 90 degrees because of perpendicular, so it's going to be 1. Okay? Times 1. So from here, we get a formula for normal component an. An equals, it's a velocity cross acceleration over speed, length of cross product over this, or in terms of r prime, r double prime, r prime cross r double prime over length of r prime, and magnitude on top and magnitude. So to find tangential component, what we'll do is, instead of multiplying by v doing cross product, we'll do dot product with v. What's the idea? Because v is going to be parallel to t, and t is perpendicular to n, so v and n will be perpendicular, and if you do dot product, that part will disappear, and you will have only the first part. So let me want to move on to the next page. So if I take at times t plus n times n, which equals to acceleration, and I multiply it by velocity. Okay. Dot product. So then P dot A equals V dot ATT plus V dot ANN. This part equals to 0 because V is parallel to T, which is perpendicular to normal vector. So V is essentially your unit tangent vector. The only difference is magnitude. The first part, that is essentially magnitude of velocity speed times T multiplied by ATT. T times T is going to be 1 because length of T is 1. So it's going to be equal to AT times V. So what we got in here is left side is V dot product A equals to magnitude of V times tangential component. And then we're going to solve it for AT. And that's going to be what we're looking for. Okay, so we get A tangential equals to dot product velocity and acceleration divided by speed. So it equals to R prime dot R double prime over length of R prime. And again, similar formula for normal component. You essentially do the same, something similar. So R prime cross R double prime, and you want to take it magnitude divided by length. Okay. Usually T is reasonably easy to find. Normal vector, if we are on a plane, it's also easy to find. But in three-dimensional space, normal vector, usually it's difficult to find. Then we kind of will go around to find normal vectors. So often, whatever we mean by word often, maybe more than 50% of the time, to find normal vector, we'll say it's essentially it's your acceleration minus ATT divided by A. Okay. So often that's how we're going to define a normal vector. Again, often doesn't mean necessarily all the time. It's idea, but maybe that's another way how you can find it. Sometimes you find it from definition. If you know what T prime, then you find it from the definition. Just basically make it unit, right? So another way, if you can easily find what T prime is, if you know T prime, then your normal vector is essentially unit vector in the same direction. So if T prime is difficult to find and you don't see an easy way to simplify that expression, especially if object doesn't move with constant speed, then you probably want to stick to this way. Okay. Find oscillating circle. To y equals x squared at x equals to 2. All right, let's see what I mean by that. So we have our parabola. So we have our parabola. Okay. Then we have our point x equals 2, y equals to 4. Then we have tangent vector. Tangent vector. Then we have normal vector. Okay. Firstly, is it obvious to you that normal vector is to the left and not to the right? Because it bends this way, so normal vector will go with the direction of bending, so with the direction of acceleration. Because it bends this way, curve bends to the left, so your acceleration vector will be bending to the left, so your normal vector also will be to the left. That's an idea, okay? So we just visualize it. Okay. And because we are on a plane, so everything will be happening on a plane. So we're not leaving that plane, okay? So usually if we're talking about real three-dimensional curve, then, you know, our plane will be approximation of what is happening locally. Because we have everything on a plane right now, so everything just stays on the plane. So are your acceleration on the plane, on the same original plane, your tangent on the same plane, your curve on the same plane. So everything, nothing moves in the plane. So everything is two-dimensional. So far, so good? Okay. What we do? We find the radius of oscillating circle. So we find the radius, which is going to be 1 over curvature. Okay. So along the normal vector, we're going to travel from the given point toward the center and we reach it. Okay. Does that picture make sense? And that's going to be center. And again, the radius of a circle, oscillating circle, is going to be 1 over curvature. And normal vector will tell you which way to go because it's going to be perpendicular to tangent. Circle should be perpendicular to tangent. A circle and a curve, they should share the same tangent line. Okay, so we get that. And as soon as we get there, we're going to draw our circle. Then we draw our circle. And that's going to be oscillating circle we're looking for. So that's an idea. Okay, so let's do calculations. So first thing we need to do is let's write down parameterization of our curve. If you want to, or if you like, basically what I want to do is I need to find the curvature first. You can either jump to that shortcut formula which we derived last time for two-dimensional function y equals f of x. Or you can switch to parameterization and say x is x, y equals to x squared, and z equals to 0. So I'm not sure. To x squared 0, r prime equals to 1, 2x, and 0, r double prime equals to 0, 2, 0. Then cross product. Again, because we already talked about that, you r prime on a plane, you r double on the plane, acceleration velocity is on the plane. So your cross product will be sticking out from the plane. So x coordinate and y coordinate will be equal to 0 because it has to be perpendicular. So only one which is left to calculate is the last one. So I believe it's going to be 2. Okay. Magnitude of velocity, magnitude of r prime is going to be square root of 1 plus 4x squared. Because we're doing at x equals to 2, so it's going to be square root of 17 if I'm correct. Square root of 17. Okay. So then radius is going to be, so curvature is going to be equal to r prime cross r double prime divided by velocity cubed. That's the formula, right? That's the one which we wrote the last time. R cross r double prime length is going to be 2 divided by square root of 17 squared. So k was equals to 2 over 17 square root of 17. So radius will be opposite of that, reciprocal, I mean, 17 root of 17 over 2. Okay. Now, at x equals to 2, velocity is, so let me, should not be too difficult to find unit vector. It's 1, 4, 0 over square root of 17. Because we actually already found the speed. Tricky part. Because we are working on a plane, we can take advantage of the thing that we are working on. So we're working on a plane. We're working on a plane, so we should be staying on the plane, right? Now just imagine you have your vector 1 and 4 essentially, and you don't worry about your 0 coefficient because 0 with z equals to 0, it will be still 0. Essentially, we look at 1 and 4. If you like, 0 at the end. We are looking for this guy, which is right here. Right? So we are looking for normal vector, but firstly, let's find something in the same direction. So the first thing we'll do, we'll find direction, and then we'll take care of unity. Unity should be easy to take care of. So that's what we're looking for. And it's easy to eyeball what this vector is. So let me put that maybe on the next page. Okay, and then we'll return to that picture. So if on a plane, if I give you vector x, I guess with 2 coordinates, x and y, or 1, say 2, then it's easy to guess the vector which is going to give you dot product. So we're looking for something so such that the dot product is going to be 0. So what we do is, so we're looking for 1 times x plus 2 times y. And that's supposed to be equal to 0. So what we often will do, we will going to flip 2 and 1, and we're going to negate one of them. So b, which equals to flip it and put minus, or flip it, put minus here. That works. Okay. So when we're talking about two-dimensional vector, it's easy to see 2 vectors which are going to be perpendicular to it. All what you have to do, just flip the coordinates, put minus. Is that obvious? So that's what is happening in the plane. On next one. So on XY plane, it's easy to find perpendicular vector. Okay, now let's return to the previous page. We know that vector is 1, 4. Then we can potentially find 2 vectors perpendicular to it. So perpendicular to 1, 4, 0 are going to be R. You flip 1 and 4, you put negation. You flip 1 and 4, you put negation. So those are our 2 potential candidates. If there are no questions, then let's finish it up. So which one are we going to pick, first or second? Let's look at our original picture right here. So you see, we wish the vector to be moving to the left. You see it right here. Now let's see what we've got. here, which of these vectors is going to be moving to the left? So moving to the left means x is going to be getting negative, right? So x will be negative. So this one, second one, goes to the left. Okay. And then essentially, you know what normal vector is? It's essentially a -4 and 1 and 0. All that you have to do is just take and divide by its magnitude. So we have our point on a curve 2 and 4. We have our curve, parabola. And when from this point, we want to travel toward the center. And you remember the distance is going to be 17 root 17 over 2. So on here, we know our normal vector. Okay. Now to find center. So what do? We start somewhere at the origin somewhere here. So what we do is we travel to 2, 4, and then we travel to the center. Okay, so that's how we're going. We're not going to travel directly to the center. We do it as a sum. So to find the coordinate of the center, we need to travel to a 2, 4 firstly, plus, and from 2, 4, we want to travel to the center, plus, from 2, 4 to the center, and to travel from 2, 4 to the center, we're going to travel parallel to n, and that's going to be n normal vector. But normal vector will give you magnitude only 1. So what we'll do is we multiply it by the distance we need to travel. So that's how we're going to find center. Okay, so what we got for center? So 2, 4 plus. You recall from the last page that a normal vector will have coordinates -4, 2 divided by square root of 17 times 17 square root of 17 over 2. Square root 17 cancels out. So we have 2, 4 plus 17. -4 over 2 is -2. 2 over 2 is 1. So finally, we have our center. 2 plus -34 is -32. And 4 plus 17, 4 plus 17, 21. So we got center, we have radius. 17 square root of 17 over 2. And if you know that piece of information, we should be able to write down the equation of the latency. So x plus 32 squared plus y minus 21 squared equals to 17 cubed over 2 over 4. Okay, something like this. At least that's what I could